Now we will see the term right hand thread and the left hand thread. Here in this diagram you can see the two diagrams which is first one is the right hand thread and left hand thread. So we will see now which one is the right hand thread and how to recognize the right hand and the left hand thread. So right hand thread is what? When the axis of the screw is vertical and if the thread slopes upward from left to the right is known as right hand thread. Here you can see in this diagram the axis of the screw is a vertical and the thread slopes from downward to the upward direction from left to the right, and this particular arrangement is called as a right hand thread. Now next is a left hand thread. Now when the axis of the screw is a vertical, in this diagram you can see the axis is the vertical, and if the threads slopes downward from left to the right, here you can see the threads slopes downward from left to the right is known as left hand thread. So in right hand the threads are slopes in upward direction from left to the right, and in case of left hand thread the slopes downward from left to the right. So these two arrangements are the most important to know the which type of a thread it is. Now next term, multiple thread screw. So when the desired axial movement is a maximum at the same dimensional screw, then the number of threads of the identical pitch will be manufactured side by side on the rod. So the multi-start threads are used when large lead with a fine thread of high efficiency is required, and the multiple start threads are of double, triple or quadruple start type of a screw. So these are the various, you can say, the terminologies of the power screw. So now the next term is the thread profile used for the power screw. So now the first one is a square thread. So we will first see the definition and then the diagram. The flanks, in case of a square thread, the flanks are 90° with the axis of the screw. The flanks, or you can say the teeth profile of that particular screw is 90° with the axis of the screw, and this such type of a arrangement is called as a square thread. So the force is applied on both sides, means force is applied on both sides when they are meshed with another square type of a thread. So the force will be applied on the both sides and it will transmit the power without any side thrust, and they are generally used in a screw jack and clamping devices. Now the next term, that is trapezoidal thread. Now what is trapezoidal thread? When the flanks are 30° with each other. Here in this diagram you can see the teeth profile, or the two teeths are having 30° with each other. So this arrangement is called as a trapezoidal thread. Okay, again it is used in machine tool, lead screw and power transmission devices, and they are manufactured on thread milling machine with a multi-point cutting tool. Now the next term, acme thread. So in case of acme thread, the flanks are 29° with each other. So earlier in trapezoidal thread the flanks are 30°. In case of acme thread it is 29°. Here you can see. So the force applied on both sides in this also used in machine tool, lead screw and power transmission devices. Again they are manufactured by dies, hence easy to manufacture, and efficiency is less than the square thread. So the next term, that is buttress thread. So in that case the flanks or the teeths are inclined at 45°. Here you can see the arrangement. The teeths are 45° to the each other, and it can be take thrust in one direction only, and it is used in vices and clamping devices, and they are stronger than the other types of threads because of the teeth profile. So here, there are the basically four thread profile generally used for the power screw. The first one is the square thread. The flanks are having 90° with the axis of the screw. The trapezoidal thread, the flanks are 30° with each other. Here you can see. In case of acme thread, the flanks are 29° with each other, and in case of buttress thread the flanks are 45° with each other. Now in next term we will see the reasons for using the square thread in a power transmission. So why only square threads are used for the power transmission? What are the reasons behind it? So it is having a greatest efficiency due to 0° profile angle. It produces the minimum radial or bursting pressure on the nut. It transmits the power without any side thrust on the both side, and more power transmission because of the less friction. Then the next one is a smooth working and a noiseless. So these are the various, what you can say, the reasons for using the square thread. If you see, there is, what you can say, there is a side thrust on both sides in case of a trapezoidal thread, acme thread, or buttress thread, but in square thread case there is a no any side thrust. So that's why square threads are more used in a power transmission, and it is having again smooth working and noiseless working also. Now the next is reasons for using V threads for the fasteners. So it is having a greatest efficiency due to 0 degree profile angle. It produces minimum radial or bursting pressure on the nut. It again transmits the power without any side thrust on both sides, and again it is having more power transmission because of the less friction, and again it is smooth working and noiseless. So more or less the properties of square thread or the V threads are same. That's why in V threads are used in fasteners, and the power threads are square threads are used in a power transmission. Now we will see the difference between V threads and the square thread, the basic difference. Here are the various points. Here is the V thread and the square thread. If you see about the profile angle, in case of V thread it is 60 degree, but in case of square thread it is 0 degree. Strength of the V thread is high due to the thickness of the thread at a base, and in case of a square thread it is the strength is less due to the thickness of a thread. Again the load carrying capacity is more in case of V thread due to the profile angle. Again in case of a load carrying capacity of the square thread it is less. Efficiency is again less in case of V thread due to high friction. Again in case of a square thread it is high due to less friction. The radial pressure in case of V thread is subjected to the radial pressure, and it is no radial pressure in case of a square thread. Manufacturing is very easy for the V thread. For the square thread it is difficult one, and the cost in case of V thread it is very cheap one, and in case of square thread it is costly because the manufacturing is difficult. Now we will see the torque required to raise the load. Now in this diagram we will see the diagram. In this diagram here you can say this is what the thread profile and having angle alpha, and here is what you can say the load, and it is going to be raised, or you can say the motion of this load is in vertical upward direction from left to the right, means that the load we have to raise. Now here you can see W is the weight of that particular load. Then here is what motion is in vertical direction, so the frictional force will be the against the motion, so it is denoted by F is equal to mu Rn. And here is what P is what the effort which is required to raise this load. So again if we resolve that P, then in upward direction P cos alpha, in downward direction P sin alpha, and that normal reaction is always against to that what you can say against to that load, and it is denoted by Rn. So for load raise, for loading the raise, and effort P, here I will shown effort P is applied on the nut, and for one complete revolution of the nut screw will move axially. So the forces acting on the thread profile are as shown in figure. So here you can see, and resolving the forces along the plane of the thread profile as shown in this figure. Now we will see one by one. If you take, when we take summation of f of x, so that is summation of all the horizontal forces. So what are the horizontal forces here? That is P cos alpha, here is W sin alpha, and mu Rn. Here these are the three what you can say the horizontal forces. Okay, so P cos alpha is a positive one. Let's say it is in a clockwise direction, that's why it is positive. Here is W sin alpha and mu Rn, that is frictional force, is in anti-clockwise direction, so that's why these two are the minus from the P cos alpha is equal to 0. So P cos alpha is equal to W sin alpha plus mu Rn, and it is called as the equation number 1. Now resolving the first forces normal to the plane of the thread profile. Here is what summation of all the vertical forces taken. So if you take the summation of all vertical forces, here is what Rn, it is going upward side, so upward direction we will consider as a positive. Then minus P sin alpha, it is going in downward direction, that's why here is negative sign. And W cos alpha, again it is going in negative direction, that's why it is minus W cos alpha. So Rn is equal to what? P sin alpha plus W cos alpha, that is equation number 2. Now substitute that equation number 2 in equation number 1, means Rn value we will put in that equation. Now we will see what equation will takes place. So if we put that, what will happen? P cos alpha is equal to W sin alpha plus, here is what, mu into, here we have put the Rn value, that is P sin alpha plus W cos alpha. So P cos alpha is equal to W sin alpha. Just we will resolve that term. We will multiply that mu with the inside bracket terms, mu P into sin alpha plus mu W cos alpha. Then P cos alpha minus mu P sin alpha is equal to W sin alpha plus mu W cos alpha. Just we are rearrange the term, mu P is goes to the left hand side. So P cos alpha minus, now the P term have taken common, cos alpha minus mu sin alpha in a bracket is equal to W again here taken as a common. So in bracket sin alpha plus mu cos alpha. So P is equal to what? W into sin alpha plus mu cos alpha divided by cos alpha minus mu sin alpha. So we know mu is equal to tan phi, that is frictional coefficient mu is equal to tan phi. Phi is the friction angle. So tan phi is equal to sin phi upon cos alpha. That relation we already know. So just by putting in above equation, P is equal to W into sin alpha plus mu. Mu is what? Sin phi by cos phi into cos alpha divided by cos alpha minus. Just by putting that mu term over here in this equation, we will get this equation. So P is equal to W into sin alpha. Now just by multiplying and rearranging the term, sin alpha into cos alpha plus sin phi into cos alpha divided by cos phi. Now cos alpha into cos phi minus sin phi into sin alpha divided by cos phi. Now that cos phi term will get cancelled, and finally P is equal to W into that remaining term. Now just by trigonometric relation, we will know that P is equal to W into sin alpha plus phi. The resolution of these two equation by trigonometric relations divided by sin alpha plus phi divided by cos alpha plus phi. Now P is equal to W, as sin by cos is tan alpha plus phi. So this is what the torque. Now this is the P is what the effort which is required to raise the load. Now we will see the torque required to overcome the friction between screw and nut. Now T1 is equal to that P into perpendicular distance. So T1 is equal to P into perpendicular distance or the radius, okay, and radius is nothing but diameter by 2. So T1 is equal to P is what, means, or torque, you can say torque is equal to effort into radius. So torque T1 is equal to effort is what, W into tan alpha plus phi into dm by 2. When the load is taken by the thrust collar, so that load should not rotate with a screw, then torque required to overcome the friction at the collar is, so according to the uniform pressure theory and according to the uniform wear theory, we can find out that load is taken by the collar. Okay, so T2 is equal to 23 into 2/3 into mu1 into W into R1 cube by R2 cube minus RT cube divided by R1 square minus R2 square. So by according to the uniform pressure theory, we can use this formula, and according to the uniform wear theory, we can use this formula, that is T2 is equal to mu1 into W into R, where T2 is equal to mu1 into W into R. R is what, the mean radius, where R1 plus R2 by 2, where R1 is the inside radius and R2 is the outside radius of that particular collar. And the total torque required to raise the load is T is equal to T1 plus T2. So if you want to find out overall torque required to raise the load, T1, here it is T1 plus T2. When we will use this equation, if there is a collar available. If collar is not available, then there is no need to use these equations. Only you can find out the torque required to overcome the friction between screw and nut. If the collar is available, then you can use these two formulas, and according to requirement, if they say use the uniform pressure theory, you can use this formula. If they say use the uniform wear theory, you can use this formula. Now as we have seen the torque required to lower the load, now we will see the torque required to lower the load. Now we have to lower the load, so how much torque will be required to lower that load, we will find out. Now here is same diagram. only motion is in downward direction. In earlier the motion was in vertical direction because we want to raise the load, but here in this case the motion will be in downward direction as we need to find out the torque required to lower the load. So the motion is in downward direction, so the frictional force will be opposite to the motion. All other terms are as it is. Now here effort is will be in, earlier it was effort was acting to the right direction because required to rise, but here in this case the effort is to the left side because we are lowering the load. Now here for load lower, an effort P is applied on the nut, and for one complete revolution of the nut, screw will move axially. The forces acting on the thread profile are as shown in figure. So by resolving the forces along the plane of the thread profile, so first we will take summation of f of x, that is summation of all the horizontal forces. So if I take, that is P cos alpha, now it is in anti-clockwise direction, so minus P cos alpha, and again minus W sin alpha, again it is in anti-clockwise direction, but that mu Rn is in clockwise direction, that's why here is plus mu Rn is equal to 0. So P cos alpha plus W sin alpha is equal to mu Rn. So these are the summation of all the horizontal forces. Now resolving the forces normal to the plane of thread profile, that is summation of all the vertical forces. So summation of f of y is equal to 0. So if we take the summation of all the vertical forces, here is Rn going upward direction, so positive, plus P sin alpha, that is here is P sin alpha, again it is going upward, that's why positive 1, and minus W cos alpha, again it is going downward direction, that's why it is minus W cos alpha. So Rn is equal to W cos alpha minus P sin alpha, that is equation number 2, that is summation of all the vertical forces. Now substitute equation 2 in equation 1, just we can put same as it is, just we can put that Rn value in equation number 1. What we will get, P cos alpha plus W sin alpha is equal to mu into Rn is what, W cos alpha minus P sin alpha. So by again rearranging the term, here you can multiply that mu in bracket terms, mu W cos alpha minus mu P sin alpha. So P cos alpha, just we will take P terms to the left side, W terms to the right side. So P cos alpha plus mu P sin alpha is equal to mu W cos alpha minus W sin alpha. So just by taking P as a common, so P into cos alpha plus mu sin alpha, and again taking W as a common, W in bracket mu cos alpha minus sin alpha. So just we will take that P term to the left side and other terms to the right side. So P is equal to W into mu cos alpha minus sin alpha divided by cos alpha plus mu sin alpha. So and same as it is, that mu is friction coefficient is equal to tan phi, which is of sin phi upon cos phi. Again by putting this mu value over here, we will see the next term. So by just putting the values over here, we will get this equation as P is equal to W into sin phi upon cos phi into cos alpha minus sin alpha divided by cos. Just by putting the mu value, that is sin phi upon cos phi in earlier term, we will get P is equal to, now again multiplying these all terms and resolving the equations, again we will get this equation. So by cancelling cos phi only these two terms will be remaining, and then again P is equal to W into sin phi minus alpha cos phi minus alpha, and again by trigonometric relation P is equal to W into tan phi minus alpha. Now again torque required to overcome the friction between screw and nut, as we know torque is equal to effort into radius, where radius is dm by 2. So T1 is equal to P into dm by 2. So P, as we already known, W into tan phi minus alpha into dm by 2. Now again if there is a thrust collar is present, then when the load is taken by that thrust collar, so that torque so that the load should not rotate with the screw, then torque required to overcome the friction of the collar, again uniform pressure theory and uniform wear theory. So T2 is equal to 2/3 of mu1 into W into R1 cube minus R2 cube by R1 square minus R2 square, or again according to the uniform wear theory, T2 is equal to mu1 into W into R, where T2 is equal to mu1 into W into R is what, it is a mean radius, so R1 plus R2 by 2, that is inside radius and outside radius of the collar. So now the total torque required to raise the load is what, T is equal to T1 plus T2. Now we will see about the next term, that is efficiency of the screw. Now what is efficiency? It is the ratio of ideal effort to the actual effort required to raise the load is called as a efficiency of the screw. So it is the ratio of ideal effort to the actual effort, and we know that the actual effort required to raise the load is what, as already we have known the equation, P is equal to W into tan alpha plus phi. That is what the actual effort required to raise the load. Now for the ideal effort, there is a no friction between nut and screw, so that's why phi is equal to 0. So the coefficient of friction, angle friction is of 0, as there is a no friction. So therefore the ideal effort is required, P0 is equal to what? W into tan alpha, as phi is 0. So only tan alpha term will be there. Hence the efficiency of the screw is what? It is the ratio of ideal effort to the actual effort, and this is the P0 by P into 100. Now percentage efficiency is equal to what? P0 is what? W into tan alpha divided by W into tan phi plus alpha into 100. So by using this equation you can find out the efficiency of the screw. Now the next term, the overall efficiency of the screw. Now what is overall efficiency of the screw? It is the ratio of ideal torque to the actual torque, and which is required to raise the load is called as the overall efficiency of the screw. So we know that the actual torque required to raise the load is what? T is equal to T1 plus T2, that already we have known, where T1 is equal to what? P into radius, that is effort into radius, where P is what? W into tan alpha plus phi into dm by 2. Now according to the uniform pressure theory and according to the uniform wear theory, these two equations already we have seen. So in case of ideal torque, the friction between screw and nut collar is absent. That's why phi is equal to 0. So mu1 is equal to tan phi, and tan 0 is what? 0. So your mu1 value will be what? 0. So T0 is what? T0 is W into tan alpha into dm by 2 plus 0. Where T0 is what? T1 plus T2. Right? T1 is what? W into tan alpha plus phi into dm by 2 plus T2 0. Why 0? Because mu1 value is 0, so whole term will get it 0. So that's why your T0, that is ideal torque, will be 0. 0, not 0. It is ideal torque will be W into tan alpha into dm by 2. So the percentage efficiency is what? Ideal torque to the actual torque into 100. So the T0 is the overall efficiency. So the equation will be for overall torque, you can say W into tan alpha into dm by 2 divided by T is what? T1 plus T2 into 100. Now the next term, that is self-locking and overhauling of the screw. These two terms are the most important. What is self-locking and what is overhauling? So the self-locking and overhauling of the screw terms are related with the lowering of the load, as we know that the effort required to lower the load is P is equal to W into tan phi minus alpha. Already we have seen the torque which is, or the effort which is required to lower the load. The equation is this one. If it is to raise the load, P is equal to W into tan phi plus alpha. Also we know that the torque required to lower the load is what? T1 is equal to effort into radius, that is W into tan phi minus alpha into dm by 2. But in above equation, if friction angle is less than the helix angle, means friction angle is what? Phi, and alpha is what? Helix angle. If phi is less than alpha, then effort and torque becomes negative, means here phi value is less than the alpha, then here you effort whatever you will get, or the torque value you will get, is what? Negative. So therefore the load works positively and starts moving downward without effort and torque. So this condition of the screw is called as overhauling of the screw, means without any what you can say, without any effort it will downward without any effort and without any torque. In that condition of the screw is called as the overhauling of the screw. However, in above equation, if friction angle is greater than the helix angle, means phi is greater than alpha, then effort and torque becomes positive. If phi value is less, the torque value will be negative. If phi value will be greater, then torque value will be positive. So in that case, the load works positively and effort is required to lower the load. So this condition of a screw is called as a self-locking of the screw. In earlier case, if it is of negative, there is not any effort or torque is required, but the T1 value will be positive. In that case, you require effort to lower the load, and that condition is called as a self-locking of the screw. As we know that the efficiency of the screw is what? Tan alpha upon tan phi plus alpha. Then for self-locking of the screw, phi should be greater than alpha, right? Because self-locking of the screw, phi should be greater than alpha. So therefore substitute alpha is equal to 5 in above equation. What will get? Tan, instead of alpha we'll put phi, tan phi upon tan 2 phi. So efficiency is equal to tan phi upon tan 2 phi is what? 2 tan phi upon 1 minus tan phi square. So 1 minus tan phi square will go to the numerator, that tan phi will get it cancelled and it is divided by 2. So efficiency is equal to 1 by 2. If we resolve it, it is 1 by 2 minus tan phi square by 2. So means what? 1 by 2 means what? 0.5 minus tan phi square by 2. So that equation indicates that from above equation it is observed that for self-locking of the screw, the machinery efficiency should be less than 50%. Already here 0.5, whatever the value it will get minus from 0.5. So it is obviously your efficiency will be always should be less than 50%. Now we will see the various types of stresses in a power screw. So the first one, the direct compressive stress due to the axial load. So the equation for the direct compressive stress is sigma c is equal to P upon pi by 4 dc square, where P upon area of that particular screw, that is pi by 4 dc square. Now the torsional shear stress, the equation for the torsional shear stress, T is equal to pi by 16 into Q into dc cube, where Q is equal to 16 into T divided by pi dc cube. Then third one, the principal stresses, when the screw is subjected to the direct compressive as well as the torsional shear stress simultaneously, hence the principal stresses induced in a screw. So according to the maximum shear stress theory and according to the maximum normal stress theory, so there will be two formulas. So according to the maximum shear stress theory, Q max is equal to 1 by 2 square root of sigma c bracket square plus 4q square, and according to the maximum normal stress theory, sigma max is equal to 1 by 2 sigma c plus 1 by 2 in square root sigma c bracket square plus 4q square. So just you need to mug up these formulas to find out the various types of stresses in a power screw. Now the fourth one is the transverse shear stress due to the axial load. So Q of the screw is equal to P upon pi into dc into n into t, where Q of nut is equal to P upon pi into d0 into n into t. Now fifth one is the bearing pressure. What is bearing pressure? A screw thread is subjected to the localized compressive stress at a profile or at a teeth or a flank of the thread of a nut on the screw. So also both threads in a relative motion while lowering and raising the load. So the formula for the bearing pressure, Pb is equal to P upon pi by 4 d0 minus dc square into n. So by using this formula you can find out, or again you can use this formula also, Pb is equal to P into pi into dm into n into 2. So according to the whatever the data given in the problem definition, accordingly you can use and you can find out the bearing pressure, where T is what? The thickness of the width of the screw thread, and you can calculate T is equal to P by 2. That thickness you can find out by dividing to the pitch by 2, and n is what? The number of threads of the screw engaged in a nut. So by how will you find out n? It is of height of nut divided by pitch of thread, that is n is equal to h upon p. So by using this relation you can find out here and the T, and you can put over here and you will get the bearing pressure value. I am very thankful to all by listening to these lectures. Thanks to all.